Hello, Dan Adulkowski here from howtomechatronics.com. In this tutorial, we will learn what capacitor is, how it works, and take a look at some basic application examples. There is almost no circuit which doesn't have a capacitor on it, and along with resistors and inductors, they are the basic passive components that we use in electronics. A capacitor is a device capable of storing energy in a form of electric charge. Compared to a same-size battery, a capacitor can store much smaller amount of energy, around 10,000 times smaller, but useful enough for so many circuit designs. A capacitor is constructed out of two metal plates, separated by an insulating material called dielectric. The plates are conductive and they are usually made of aluminum or other metals, while the dielectric can be made of any kind of insulating material, such as paper, glass, ceramic, or anything that obstructs the flow of the current. The capacitance of a capacitor, measured in farads, is directly proportional to the surface area of the two plates, as well as the permittivity of the dielectric, while the smaller the distance between the plates, the greater the capacitance. That being said, now let's take a look how a capacitor works. First, we can note that a metal typically has an equal amount of positively and negatively charged particles, which means it's electrically neutral. If we connect a power source or a battery to the metal plates of the capacitors, a current will try to flow, or the electrons from the plate connected to the positive lead of the battery will start moving to the plate connected to the negative lead of the battery. However, because of the dielectric between the plates, the electrons won't be able to pass through the capacitor, so they will start accumulating on the plate. After a certain number of electrons accumulated on the plate, the battery will have insufficient energy to push any new electrons to enter the plate because of the repulsion of those electrons which are already there. At this point, the capacitor is actually fully charged. The first plate has developed a net negative charge and the second plate has developed an equal net positive charge, creating an electric field with an attractive force between them, which holds the charge of the capacitor. Let's take a look how the dielectric can increase the capacitance of a capacitor. A dielectric contains molecules that are polar, which means that they can change their orientation based on the charges of the two plates. So, the molecules align themselves with the electric field in such a way enabling more electrons to be attracted to the negative plate, while repelling more electrons out of the positive plate. So, once the capacitor is fully charged, if we remove the battery, it will hold the electric charge for a long time, acting as energy storage. Now, if we shorten the two ends of the capacitor through a load, a current will start flowing through the load. The accumulated electrons from the first plate will start moving to the second plate until both plates become back again electrically neutral. So that's the basic working principle of a capacitor, and now let's take a look at some application examples. Decoupling capacitors or bypass capacitors are a typical example. Decoupling capacitors are often used along with integrated circuits and they are placed between the power source and the ground of the IC. Their job is to filter any noise in the power supply, like voltage ripples which occur when the power supply for a very short period of time drops its voltage, or when a portion of a circuit is switched causing fluctuations in the power supply. At that moment, when the voltage drop occurs, the capacitor will temporarily act as a power supply, bypassing the main power supply. Another typical examples are capacitors used in DC adapters. For converting the AC voltage into a DC voltage, a diode rectifier is usually used, but without the help of capacitors, it won't be able to do the job. The output of a rectifier is a waveform. So, while the output of the rectifier rises, the capacitor charges, and while the output of the rectifier declines, the capacitor discharges, and in that way smooth the DC output. Signal filtering is another application example of capacitors. Because of their specific response time, they are able to block low frequency signals, while allowing higher frequency to pass through. This is used in radio receivers for tuning out undesired frequencies and in crossover circuits inside speakers for separating the low frequencies for the subwoofer and the higher frequencies for the tweeter. Another rather obvious use of capacitors is for energy storage and supply. Although they can store considerably lower energy compared to the same size battery, their lifespan is much better and they are capable of delivering energy much faster, which makes them more suitable for applications where high burst of power is needed. So that would be all for this tutorial, but you can always find more details and tutorials on my website howtomechatronics.com. Thanks for watching and don't forget to subscribe.